Thanks everyone for coming. It's my real pleasure to introduce Nikolay Malkin. So Nikolay is a Chancellor's Fellow at the University of Edinburgh and a Program Fellow at CIPA. And Nikolay and I got to know each other when we were postdocs together in Yoshia's group. And I said on the sort of internal Teams channel, felt like, there are many impressive people in Yoshia's group, but Nikolay truly stood out and often felt like he was like running the group de facto when Yoshia was really excited about GPlanet. So at the time, Yoshia was really excited about GPlanets, and I felt I didn't really understand until I read Nikolay's paper on trajectory balance, and since then Nikolay's done good work understanding all this kind of deep connections between diffusion, sampling, the various different ways of training using reinforcement learning for language models, and all the various interpretations between, which I'm excited to hear about today. Nikolay came from a math background where they did their PhD at Yale in pure math before switching over to CS, and has made a number of very deep connections between probabilistic machine learning since then. So please welcome Nikolay.
Yes, hi. Hello. Good. Perfect. Thank you for the kind introduction, and thank you to Marin and Matthew and Michele for hosting me. Can I get an idea of the audience? Who's a PhD student? Who's a postdoc? Who's someone more senior than the postdoc? And who's someone else? Yeah. Okay. I don't know what category that they belong to, but come to lunch or come meet with me, and maybe I'll come to learn that as well. So I want to talk to you today about what I've been thinking about continuous time generative models, ones which generate samples using simulation of a dynamical system like diffusion, and how these things can be used as algorithms for sampling probability distributions, specifically Bayesian posterior distributions over some variable. Now, I'll give you a summary, but first I want to say I'm not usually this late. I was supposed to be here 2 months and 2 days ago, I believe, or minus 2 days, and I couldn't help but remember the white rabbit who's always very, very late. And I was supposed to be here on the 11th of March. And I promise you, I'm not usually this late. And yes, perhaps as this is May, she won't be very mad, at least not so mad as she was in March. So what happened was this. There was a big fire in Glasgow Central Station. For some reason, this meant all the trains from Edinburgh were cancelled too, the day before. And so there was no way I could make it. Sorry about that. But now that I'm here, let's get started. So here's what I want to tell you about. This is the Center for AI Fundamentals, and nothing is more fundamental in probabilistic machine learning and statistics than the problem of sampling from probability distributions. The difference and the interesting point is how these probabilities are described to us, whether through data sets of samples, which we want to replicate, or through a density function, which we compare. And of course, the second question is how we sample, which is the whole field of generative modeling and probabilistic inference. So we'll talk a little about the sampling problem and about how to solve it using diffusion models, which are a class of probabilistic models which are becoming increasingly important in ML. And draw some connections and show some large-scale applications. No language models, no number theory. Sorry, Jason, I know it was promised. Sorry, others. And then at the end, depending on time and interest, I'll tell you about a few generalizations of what we talk about at the start, which appeared in some recent papers. Before continuing, I want to thank all my collaborators, and specifically these 3 PhD students. And much of what I'll say, especially at the end, is based on their papers which were recently published or will appear in this year's ICML. So if you find their names, you can read the papers. I think they're excellent. So this also serves as the main set of references for what I'm about to say. Then you'll find references throughout, blue for others' work, red for mine, or pink for mine. But please also interrupt with questions. And if there are very deep and technical questions, I'm happy to meet with anyone or talk at lunch or to answer email as you wish. Don't hesitate to interrupt if there's something pressing. So can we get started? I take it you heard the instruction that pressing questions require immediate interruption. Good. Right. So the sampling problem. You could say that sampling is everywhere. We've recently written a paper called Forgetting is Everywhere, so it's a play on that. Everything is everywhere now. So in statistics and probability and machine learning, we try to sample from distributions over some variable and pretend that this variable sits in some high-dimensional space, RD. And when we say sampling, as opposed to generative modeling to replicate a data set, we mean that we don't have samples that we want to copy, but rather we have a density function, which we know may be up to a normalizing constant. That's p target, and the unnormalized version is p target tilde. So we can take any x, we have an oracle who tells us the value of p target tilde of x, and we want to draw samples so that the probability of drawing a sample, the probability density, is proportional to p target tilde. So where does this problem come up? In statistical inference, when we have some data and we have a parameter and a probabilistic model relating that parameter to the data, we have a posterior distribution over the parameter given the observations. And Bayes' rule tells us that it's the density of this posterior is proportional to the product of the prior density and the likelihood of the data given the parameter. And if we sample the parameter, we can sample the models which those parameters describe. And so we can measure uncertainty in predictions on new data. So on the left, we see a picture of Bayesian linear regression, where on the left is a parameter space over the slope and intercept of this line. Here are 4 observed data points. And here's the maximum a posteriori, or maybe the Bayesian posterior predictive, they coincide. Line which minimizes squared error to those points. But the gray shaded region is an uncertainty estimate derived from a Bayesian posterior. On the right, we see an application to more interesting curve fitting. Now, of course, we can also compute Bayesian posteriors over neural network parameters, if you like this sort of thing, and many other things. But at least for the sake of example, until the middle of the talk, everything will be low dimensional. Right, so beyond Bayesian inference and pure statistical modeling, this problem appears on its own in many sciences. For example, in statistical physics and chemistry, we often want to determine the configuration that the atoms forming a molecule will occupy in space. And normally doing this requires running some complicated quantum mechanical simulation. But what we can often obtain is a proxy model which estimates the probability, maybe up to a constant, of the molecule being in a certain configuration. So we're in the setting where we can query for the value of the density, but we can't sample directly. So exactly the same. So here are 2 parameters describing the configuration of a very famous molecule, alanine dipeptide. And you see it has many modes, and we don't know where they are a priori. We can only compute the relative score associated with a given configuration. So again, we have the problem of sampling proportionally to a given density function. And of course, in machine learning, we have energy-based models which implicitly describe a distribution without telling us a way to sample from it. Now, related to sampling from a target distribution, there are other problems where we have not quite a density, but a density but a correction to a different model. So in generative modeling, we have many pre-trained off-the-shelf models, which we can take and generate samples, and we may want to condition them. And conditioning can be formulated as taking the density defined by the model we took off the shelf and twisting it. So multiplying that density by some likelihood function, which defines a twisted density from which we may want to sample. Now, that problem is closely related both mathematically and algorithmically to the first one. You can pretend that sampling with a given density is the same as twisting a kind of improper prior, which is uniform of the whole space. So sampling is everywhere and conditioning is everywhere. How do we solve this problem classically? Now, statistics has been concerned for decades with solving the sampling problem without any machine learning. And this is the whole literature on different Monte Carlo methods, which run a stochastic simulation, which asymptotically should approximate the distribution that we want. So just to name a few Monte Carlo sampling algorithms, which are probably familiar to most, one is importance sampling. So if we can't sample from our distribution p target, let's take some approximation, which we think covers it fairly well, call it Q. And let's sample from Q. And let's weight the samples we get by the ratio of p target and Q. And in ways which you can formalize, this weighted combination of samples from Q, where the weights are the ratio, forms an empirical approximation of the target distribution, which, as you take more and more particles, should become better and better. In the sense of weak convergence. The problem with such a method is that if you have to choose what proposal to sample from, and if these weights, the density of the target divided by the density of the proposal, are very small or very large, then this estimate is very bad and you need more samples to converge. So that's the problem. There's no learning involved. We just have to choose a good proposal Q, and how to do that is difficult. So another method is Markov chain methods. So we define a process, so a sequence of random variables, which evolves through time, which the particles which evolved according to which should converge to the target distribution. Here's a little video from one Monte Carlo algorithm called slice sampling with a new development, which we should put out our archive pretty soon. So particles are moving around, exploring the space and trying to sample from this banana-shaped thing. And if you look at the asymptotic distribution of particles averaged over time, they should converge to the target distribution. Now, again, the problem here is that you have to define very well the distribution from which you sample the next particle given the current one. And if that proposal is bad, then you can take a very long time to converge to the target. You can stay in a mode and never escape from it, for example. And then there is a method called sequential Monte Carlo, which forms some of the strongest learning-free samplers, which combines ideas from the first two. There, the idea is rather than trying to sample in one shot or to form an infinite chain, let's define a sequence of distributions which are progressively harder to sample from. For example, by forming log domain interpolation between some simple distribution like a Gaussian and the target, and having the particles gradually evolve so that at time n, they are following approximately the nth distribution. So here, for example, we interpolate between a Gaussian with these green particles and then gradually reach this multi-modal thing. And this way that you fill out the modes because you start out with something which is broader. So these are algorithms which don't involve any learning. Now, how can machine learning help with this sort of problem? But before that, I want to say, in each of these algorithms, the more computation you throw at it, the better the samples. This is an important property. So the longer you run your Monte Carlo chain, the better your approximation. The more samples you propose for important sampling, the better the approximation. Okay. So how can learning help? So the idea of amortized sampling is to, rather than every time you need to draw a sample running an expensive procedure, train a model so that once this model has been trained, you can use it to draw as many samples as you want at a very inexpensive. So all the cost of drawing samples has been pushed onto the cost of training, which is usually much more expensive than that of drawing a single sample using a Monte Carlo method. So this is the idea of amortization. So as a machine learning problem, what's going on? We're trying to fit a generative model knowing what target density is supposed to define, but without samples that we're trying to mimic. So formally, this can be seen as a variational inference problem, where a model with parameters theta defines a density or distribution p theta, and we have a distribution p target, and we want to make the two close in some measure of divergence, such as KL or Wasserstein or whatever it may be. So we're trying to solve a problem of matching two distributions. And what I'm interested in is cases where the approximation is not something simple that's often used in variational inference, like a single Gaussian, but the same kind of generative model, which we often use to mimic large data sets of high-dimensional samples, like language models and diffusion models for images and that sort of thing. Except the difference is, even though the model and the generative process are the same, we need to train them using only the target density, but without using any target samples. So the generative process is the same, the model, so to speak, is the same, but the learning algorithm and the learning problem is different. So match p-target using your model p theta. And lots of generative processes, in addition, are not just generating in one shot, taking noise, transforming to data, but are in some way sequential. So For instance, language models generate word by word, diffusion models denoise in a large number of steps. Yes, so this converts the variational inference problem into one of what's called hierarchical variational inference, which means that we're approximating generation by passing through a sequence of intermediate latent variables so that the marginal distribution of the final one matches the target. And that's actually how I came to this problem, through thinking about sampling discrete structures by sequential decision making, where you have, let's say, you're generating a phylogenetic tree explaining DNA sequences or generating a causal graph. You do it by sequential decision making, where each decision is computed by a neural network. So, for example, sample a causal graph by starting with an empty one, inserting an edge, inserting another edge, sampling parameters of the causal mechanisms associated. So you can kind of see that we've converted the sampling problem into something that feels like reinforcement learning, because we take sequential decisions and the next decision depends on the state we're currently in. So that's the basis for what we do next. Right, so the problem is amortization of sampling by sequential decision making, where the decision making is performed by a neural network, thought of as a policy or as a transition distribution that incrementally constructs the thing that is being sampled. Right. Questions about sampling and amortization in general, or we go to diffusion? Yes.
When you said the learning not with samples but only with density, so what do you mean by that?
Well, normally when we train a generative model, say, ChatGPT, well, it also has RL on top, but yes, actually that's a perfect example, because if you have a language model, you train it to maximize log likelihood of the data set of samples. Now, what if I have that pre-trained ChatGPT, I'm OpenAI, and I have the probability mass function associated to a given sequence, and you want a sample from that? How are you going to do that? If all you can do is query for a given.
Auto-regressively.
Okay, so how do you actually sample the first part? You'd have to check every possible word and see what density it has, and then you form the full distribution, then you sample. That's actually important sampling. Because you have to propose and compute the density.
I might have misheard. Did you say in the training that it's that you only have the density?
Yes.
Obviously, training of the generative model. So it's like if you took the ChatGPT, the large language model. So about training a generative model to sample from that then.
Well, probably training a second generative model to sample from ChatGPT. That's not a useless problem. It's actually what appears in distillation. But you should think of not something of a case of mimicking data, but something like sampling, like the examples from the start, like sampling from the posterior distribution over parameters of a model, a statistical model, or sampling a configuration of atoms in space. These kinds of things where you do not have data to mimic, but you have a score associated to anything that you can generate.
Yeah.
Right. So maybe on to diffusion, since we're 15 minutes in, right? I promised to get to the first 3 points, and after that, we'll see. Right, so sampling is everywhere. Diffusion models are also everywhere. And you've probably seen pictures like this. I expect that most of you have seen something about diffusion models, or so I was told. So they generate samples by iterative denoising. So they start with random noise. They take stochastic transitions, and eventually these stochastic transitions, the samples evolved according to these stochastic transitions, reach samples from the distribution that you've approximated. And they are everywhere in the sense that they're used for all kinds of data. Originally becoming popular in the context of image generation, like this photorealistic picture of Edinburgh. Actually, that steeple in the middle of the castle doesn't exist. That's fine. They're also used for planning, like trajectories, and for solving combinatorial optimization problems. This is a traveling salesman. This is actually from the first paper I ever contributed to on diffusion in 2022. And last year's, I guess 2 years ago now, Nobel Prize in Chemistry was awarded for an application of diffusion to protein folding. So these kinds of generative models built on the idea of iterative denoising are used for all kinds of data. many more examples that I haven't shown here. So how do they work? So formally, we have a data distribution, the samples from which here I've called X. I will change the notation for the rest. This is just to be consistent with the older literature. So say you want to generate pictures of cats. So you have cats called X. You define a process. So a process is a joint distribution over this collection of variables, which I've indexed Z1, Z2, Z3, and so on. And this process is defined by a noising kernel. So it's a conditional distribution over each slightly noisier cat, given the slightly less noisy cat. So I can sample from this distribution by taking a cat from the dataset and then going leftward in the picture, adding some noise each time. So this is a fixed noising kernel, which I've called pleft. And what you need to do in order to generate is to sample from the same joint distribution, but in the rightward factorization. So you want to find this denoising kernel, so the conditional distribution over slightly less noisy cat given slightly more noisy cat. And then once you've done that, you can generate new cats starting from this. So let's make that a little more precise. So you probably also know from diffusion that a diffusion model is underlyingly a continuous time object. It's a stochastic differential equation. And this is important because it means that we can actually sample it with varying numbers of steps. So let's have a closer look at this noising process. So it's defined by a procedure. I've now made time go forward, like increasing time when you generate. So the noising kernel goes backward in time. So it's defined by a procedure which, to get each t minus delta t, takes xt, maybe apply some linear transformation to it there, and then add some noise. So adds standard Gaussian noise independently sampled, scaled by square root of this type size. Now, you may wonder why this strange delta t square root of delta t. This is just to maintain consistency when you take delta t to 0, and because of stochastic processes reasons, this behaves stably when you take delta t being very small. So when we noise, we maybe apply linear transformation and then add the Gaussian. All right, so what do we need to do in order to fit the reconstruction or generation kernel? Well, we're going to approximate the transition in reverse, so from xt to xt plus delta t, also as Gaussian. We're just going to train that using maximum likelihood training, using the samples that we drew, using the noising process in green. So we take a data point, we sample the noising trajectory from it, so the increasingly noisy cats. We maximize the log likelihood of that trajectory just in the denoising order, so under the denoising kernel. We do that for a very long time. That's expensive training. And then at optimality, these two processes, one described by noising and the other described by the model we trained, come to coincide. So we can now generate by just simulating in reverse, so starting from a noise and then increasingly less noisy and getting a new cat that we've never seen before. Now, you probably saw some other versions of diffusion with denoising or score matching. And just because of some algebraic simplifications, in the specific case of Gaussian noising, those two things are all equivalent. But this view, where we just have a noising process defined by an arbitrary kernel, and we just fit it by maximum likelihood in reverse, is very general. And it allows to easily think of other kinds of diffusion models, like ones which don't have Gaussian noise, but say mix cats with some other kind of animal and generate by reversing that. Cats to lions. Right. So here's one way to look at what we just said. So because we're fitting the generative process by maximum likelihood to samples taken from a noising process, we're actually matching, by training, we're matching two distributions over trajectories or sequences of latent variables. And this is the same as maximizing the evidence lower bound of this big hierarchical model, which samples by the sequence of latents. And it's also equivalent to, maximum likelihood training is equivalent to minimizing KL divergence between the process defined by noising, so sampling from data and noising, and the one defined by sampling a random noise and then denoising it using the learned model. So the training that we just saw is matching in the sense of minimizing KL divergence two distributions over trajectories. That's the important thing to note. So here's a 2D picture now. Now the data points are points on this image of a cat. So here are noise samples, here are data samples. then the noising trajectories, I start at the blue points on the cat and I noise them and eventually they reach random noise. I fit a model and now I can sample it starting from random noise and I get the red points. I haven't fit the model very well. So you see the red points right here are a little noisier than the original cat. But I've done this in effect by matching two distributions over these gray curves in the picture. Yeah, and in continuous time, in kind of under ideal conditions, this learning problem can be reduced to denoising and to-score matching, which are other familiar formulations of diffusion models. Okay, but now recall, we are trying to solve the problem of sampling from a distribution where we only have the density function up to a normalizing constant, but no samples. Now, whatever the model that we want to train, that is going to sample from that, is a diffusion model. This KL divergence, which we wrote down before, can't be optimized anymore. Because if you think about what it is, it involves an expectation over the target distribution. So you have to sample from the target distribution, take a noising trajectory starting from it, and maximize its log likelihood under the generator. And because we don't have samples from the target, we can't do that. So you can't just train a diffusion model to sample from a distribution if we don't have samples from it. So what do you do? Well, it becomes that hierarchical variational inference problem, sampling by sequential decision making. And I found my first type of extra space. Right. So how do we solve it? Well, one option is to take the KL and do the opposite direction of KL instead. So KL divergence between the generative process, which starts with a noise and then follows some fixed number of steps, the generation kernel, and the target distribution. Now, if you write down this this KL divergence, then you actually do, you know it exactly, well, up to that normalizing constant that you don't care about of the target distribution. So this is one option. So you can write that down as an expression in terms of all of the noises that you inserted while sampling, and you can optimize that divergence directly. Now, the problem with that is the reverse KL has a kind of mode-seeking behavior, which means that if it models one mode of the target distribution, it has trouble escaping from it and going to others without passing through regions of a high loss. In addition, because to optimize this, because the sample from the generative process depends on all the noise samples you injected along the way. So when you're sampling from a diffusion model, every step you sample Gaussian and you scale it and you add it. So you need to store the entire computation graph of sampling the trajectory if you want to do backpropagation. And if the model is big and you have many steps, which often you do, then this is prohibited. Now, there are many other approaches to solving this problem other than reverse KL. I have many slides about that, but we don't have time. So if you're interested, I can talk for a long time about them. Ask me. And many of them have interesting behavior when you treat them as not n-step samplers, but take the limit as you go to continuous time. But we specifically focus on what we call off-policy divergences, which I'll tell you about next. So just to repeat, the problem is that we can't train a diffusion model to sample from a distribution with a normalized density function the normal way because we don't have samples. We sometimes can't use a reverse KL because of mode collapse issues and because it requires backprop through the entire generation. So we want to do something else. So I'll show you one way to do that. Unless there are questions here. Right. Okay, so here's an example of a different divergence you can use. So think about what the reverse KL divergence is. It's expectation over the generation process of the log density of generation divided by noising. So here I've just added a constant and put a square in it. So let's look at this expression. What stands here? So in the numerator is the probability of taking a trajectory, so a sequence of latents, which are called x0, x1, and so on, up to xn, where xn is the sample we've drawn and x0 is a noise. So in the numerator is the likelihood of getting that trajectory from p target and then following the noising kernel. So p target of xn times the product of transition densities in the noising direction. And in the denominator, we have the likelihood of that trajectory in reverse order. And because we want to make those two distributions over trajectories coincide, we want this to be 0 for every trajectory. So the log ratio should be 0 for every trajectory. Now, the problem is I lied to you a little bit, and we don't actually know the target density. We know it up to a normalising constant. So we have to put that constant here, subtract it away. It comes out of the log. So we want this expression to be 0 for every trajectory. And then that means the two distributions over trajectories given by generation and given by sampling from the target and then noising to be the same. Now, so this is called a second moment divergence because the second moment of this quantity. So different variants of it, which mostly have to do with how you define the scalar at the end. One is called trajectory balance mentioned by Jason. That's where you learn this constant as well as the parameters of the generator. You can also estimate it empirically using a batch of samples. That's not particularly important. What is important, though, is that because we wish to minimize this to 0 on every trajectory, we have freedom of choice in which trajectories we minimize this on. So here I've written this expectation over some third distribution, which is not the noising distribution, not the generation distribution of our trajectories, but some third distribution P. So what is this P? So if we think of this in reinforcement learning terms, we'd call it a behavior policy. And we're free to choose it as long as it has full support and covers all the trajectories that we could possibly generate with our model. In particular, if P does happen to equal the current model which tries to generate samples, this is called on-policy training. So then we sample trajectories from our diffusion model as it's being trained. We minimize this log squared. We take a gradient step, and we repeat. So the training distribution is evolving over time. Now, if that distribution differs from the current sampler, so starting from noise and then generating using your p theta kernel, this is called off-policy training. Now, there's a magic fact with the algebraic exercise that on-policy training actually gives you the same gradient in expectation as the reverse KL, which is a thing we didn't want to minimize because it requires backprop through the whole generation through the diffusion. But this doesn't require such differentiation. It gives you a 0th order estimate of that the same gradient. Okay. So what's interesting about this, though, is that allows training off policy, meaning take trajectories for training that aren't reaching samples from the target distribution, but which come from some arbitrary other source. Why do we need this? Why do we want this? And why is it useful? Connections drop around, I skip. So think of it this way. Let's say your target distribution has several modes, and your current sampler only samples from one of them. How is it going to find the others? If you're only training your sampler on trajectories which are drawn from your current sampler, which almost always end up in the one mode it knows, then it's never going to learn to push up the probability assigned to the others. But what if we have someone who tells us there's a mode over here that you haven't seen? Then we could sample a noising trajectory from there and train our sampler on that as well. And then we'll see, oh, we assign a small likelihood to that, but the density there is big, so I should push it up. So, well, we are able to to learn from modes that our current sampler doesn't see, as long as someone can tell us where they are, which can do it in an arbitrary way. So if the current sampler doesn't cover the modes, but we have another method which somehow can find them, let's use it to define a behavior policy for training our sampler, which we can do because the distribution on which we train our sampler, the source for drawing the trajectories for training, is arbitrary. So two families of ways to do that. One is to use some ideas from reinforcement learning, which faces the same problem, where you need to explore the space and you need to be pushed into new regions of the space which you haven't seen yet. There are different ways to do that, say keeping replay buffers, giving bonuses, exploration bonuses for reaching new places you haven't seen. And the second option is to use the Monte Carlo method. So we have methods for getting approximate samples, which are very cheap. and which can be stopped at any time depending on your computation budget. Let's use them to get some pretty bad samples from the target distribution, which may still cover some modes which our sampler doesn't know. And let's use them to get noising trajectories on which to train our sampler. So these two families of methods. The two can work together. We had a couple of works where we studied this for diffusion samplers. One way you can do it, let's have a replay buffer. This is a big set of samples. And as we're learning our diffusion model, we're drawing samples from it, putting them in the buffer. And we're periodically running some Monte Carlo, some MCMC updates on those samples in the buffer, which is a very cheap step that can be done concurrently. And we're not only training on trajectories from a current model, but also on trajectories drawn from that buffer, which are coming from older versions of the same sampler, which are further refined by some local search, some Monte Carlo updates, you can say. Another way is combining with sequential Monte Carlo. I don't have time to go into full details, but there are interesting connections between the sequence of intermediate target distributions that you try to hit in sequential Monte Carlo and the sequence of intermediate target densities, which your diffusion model follows. And you can use that to learn the proposal kernels for sequential Monte Carlo and the intermediate densities as well. We just had a paper on that, which sketches this whole connection between reinforcement learning, hierarchical variational inference, and SMC, I think, pretty well. So takeaway, if you have a method which can find the modes, and maybe can find the modes better if it's initialized with something that's using your current sampler, then you should use it to help your sampler learn. Okay, maybe I'll show you this picture. Again, 2D example. I promise pretty pictures soon. We're sampling a mixture of well-separated Gaussians in the plane. Direct reverse KL minimization gets stuck, only finds a few modes. As soon as you put a replay buffer in combination with some importance sampling, it covers more of the modes. You see a similar picture on the bottom. We're trying to sample this 4 intersecting rings. If you combine this with sequential Monte Carlo as a way for drawing samples for training, it becomes even better. So exploration methods work. Right. Now I showed you 2D pictures, but let's scale it up just a little. So what can we actually sample using diffusion models trained on a normalized density function? Well, I just quickly take you through some pictures. Well, there's a related problem of taking a diffusion model treated as a probabilistic prior and multiplying it by a likelihood function, which I mentioned is essentially the same learning problem as sampling from an unnormalized density. And you can use that for all sorts of things. Okay, so let's say you have a diffusion model which samples images, say MNIST digits or CFR images. We have a classifier taken off the shelf, which gives us the probability that a given image belongs to class 7 or class dog or something. So we can obtain a new diffusion model, which is good to sample for you from the posterior distribution. So image given that it's a dog or a 7. Now, normally with a diffusion model, doing that exactly is not tractable. There are approximations. You can solve different interesting denoising problems, so Bayesian inverse problems, where you have an image which you don't see. There's an image which you don't see, and it's been distorted in some known way, say by applying some transformations and adding a noise. And you observe the result of that. Your goal is to sample the posterior distribution over what the original image was. And that's supposed to be likely both under the prior distribution given by a diffusion model and under the likelihood model. So it's supposed to be likely to generate the thing that you eventually observed. So we can train diffusion models to do that using the off-policy RL methods of the objectives I showed you before. Here's a real application with some images taken from a telescope of galaxies which have been distorted by a process called gravitational lensing, where the rays of light coming from the galaxy are distorted by some very heavy object in the middle, like bends. But you know what clean galaxies look like. You want to restore the original one from the noisy observation. Many other applications, including language models, text, RL, Bayesian optimization, and so on. Have a look at the paper. Okay, Another thing which I'm quite excited about is, well, here I just showed you sampling posteriors under diffusion model priors. What if the prior is some other kind of generative model? And this brings us to what I call outsourced sampling. In the sense of, if you've heard noise the noise outsourcing lemma. So writing a generative model as a function of a deterministic function of a random noise. So think of a generative model, call it P of X, which is represented by a deterministic transformation of a random variable following some known noise distribution, like Gaussian. Think of a GAN or something. Now, a GAN generator generates samples by drawing a random noise and pushing it through the generator and outputting the result. Now, GAN famously does not define a density that you can compute over the target space, usually because it's concentrated on a lower dimensional manifold and because there is no guarantee that two different noises will give you two different samples. So GAN does not directly give you a density of the target space. But what if we want to treat the distribution given by, say, a GAN as a probabilistic prior? Or any other generative model which expresses generation as taking a noise sample and pushing it through some function, f. So probabilistic prior, meaning that we have a likelihood function, so p of y given x, and we want to sample from the posterior, p of x given y, which is proportional by base rule to p of x and p of y given x. But we don't have p of x, the density, directly. We're just able to sample. So here's the idea. Let's pull back this posterior distribution to the noise space, as I said. So it turns out that if you sample z in the noise space with a density proportional to the noise density, so like standard Gaussian over z, multiplied by the likelihood function on the decoded or generated z, f of z, if I sample from that and then push it through f, I get samples from the posterior. So instead of sampling x, which I can't do because I don't even know the density of the prior, p of x, I'm going to sample z in the noise space by twisting or tilting the original prior p of z by the likelihood function evaluated on the decoded z. So this turns into a problem of sampling a distribution over z with this known unnormalized density function. And there we can apply all the methods we saw before, like Monte Carlo methods, or training a diffusion model to sample in the noise space. So we've noise, sorry for that. We've outsourced the sampling problem to the space of z, which is maybe lower dimensional and where this posterior may be more smooth. So what can we do with this? Well, of course, we can condition generative model. We can condition GANs and hierarchical VAEs. But what I find interesting is you can use this for an RLHF application. So I don't have my... I'm reminded of lunch in 15 minutes, excellent. It's a hint to finish in 5 minutes, which I certainly will. I don't have, oh yeah, a cat riding a llama picture. So text-to-image generative models struggle sometimes with compositional queries, such as combinations of attributes which are rarely seen in training. So here, a cat riding a llama. This is, I think, this is a pretrained stable diffusion, I believe. It's not a cat riding a llama. It's a cat with llama head, or the llama and the cat are blending into each other. So models struggle to answer compositional queries. What we do have is pretty good verifiers. So reward models, which can look at an image, look at a caption, and say, do the two match? So let's use that to define a posterior distribution. So to tilt the original distribution over images by the reward function that we've taken off the shelf. And we're going to do that by learning to sample the noise space. Yes, question? Image reward, yes, it's another model. But it's a discriminative kind of model. It's trained from human feedback. It's not a generator. So we tilt the prior, and we get images which satisfy. We get a new sample. We train a diffusion model to sample in the noise space. And then those decoded samples will satisfy the verifier and be likely under the prior. Okay. Now, I don't have time to tell you about both generalizations, which I didn't think I would. But just to show you quickly, one thing you can do is not just sample from a distribution, but build bridges between two distributions. So here's the 2D picture for you. This is the Schrödinger bridge problem, and we learned to solve it in the case where we don't have samples from the distributions, but we have density functions. And so we again have a distribution evolving through time, and it evolves from one known distribution to another known distribution. What I want to show you, though, is that you can apply the same idea in latent spaces. So say, learn a mapping between all latent samples generating all pictures to only those generating, say, 5s, where you don't have any examples of 5s, but you only have a classifier of whether a given decoded latent is a 5. And so what happens when you do this on images? We learn this translation, this dynamic translation between all latents and latents representing, say, images of a given class in latent space of a GAN here. So we get this translator, like a diffusion model in latent space, which maps anything to an image of the target class, but seems to preserve unrelated attributes. So, for example, this was not a horse. It became a horse, but it stayed on a white background. Same with this bird that became a flying horse. Similarly, on the left, we see the shape is mostly preserved. Like this blob-like animal, I don't know what this is, turned into a car, which occupies about the same part of the image with the same color of background. So we have this optimal transport property in latent space for the learned dynamics. And it defines a mapping from the prior distribution to the posterior given the target class. All of this without any samples, just a pre-trained GAN, for which we don't even know the density in data space, and a pre-trained model which classifies images in the image space. Right. One more thing, just you can do the same thing in discrete space with discrete diffusion models. No time for that, but this allows you to do things like bridges in discrete spaces, and oh yes, of course, sampling in latent spaces of discrete latent variable models like VQVE. So all of the same can be generalized beyond Gaussian diffusion in RD. Okay, I better finish up then. So here's the last slide. I sketched a couple of connections, connecting the problem of sequential decision-making, an RL problem essentially, to the problem of hierarchical variational inference, meaning learning the transitions relating a sequence of latent variables so that the marginal distribution of the final variable is equal to some distribution defined only by a density with no samples. And then I showed diffusion models as a special case of that, where the intermediate latents are the noisy states in a diffusion process. And these connections allow us to do a few things. They allow us to sample from distributions, but also to take diffusion models and fine-tune them to constrain them in a way that's asymptotically exact, rather than making the kind of approximations that people often do to combine a diffusion model with auxiliary reward model. It allows us to sample in latent spaces of other models and outsource the conditioning and translation problems to those latent spaces, and thus to perform data-free translation in latent space using these stochastic bridges. I think there can be interesting applications there to different original kinds of conditioning, to image editing, style transfer, and so on. But I think the most interesting question when we have made all these developments in algorithms is not how to sample better with this model or that, or using this Monte Carlo method or diffusion model or that, but what to sample, not how to sample, but what. Because what's interesting and unique about off-policy RL algorithms for training sequential samplers is that they can both use the knowledge of the problem structure that we impose in methods like MCMC, which are good at exploring a space using known samples, and can use generalizable structure in the data that they generate in the same way that large generative models can. So big neural networks for generating things work well because they have good inductive biases and they can that allows them to generalize. But now we have samplers which can take advantage of the same generalizable structure at the same kind of scale, because they're using the same kind of generative processes, such as diffusion, as their large models do. So what can we generate with that we couldn't before is, I think, the most important question that people working on amortized sampling should be asking.